These are the lecture problems, the solved problems for Chapter 7. Take a second to read it. Here we have a spring that has been pushed backwards by some mass. That spring was initially at some position at where it was unstretched. I'm going to call that x0, and that spring has been compressed by this distance x right here. So what the spring is doing is it is applying a force to this mass. It's going to be the force of the spring. What else do I know about this problem here? I know that the spring has some constant of 25 newtons per centimeter. Being very careful, I'm going to write my spring constant to be 2500 newtons per meter. I always have to work everything in meters, kilograms, newtons, and seconds. And this force of the spring can be written as a relationship between how far it was compressed and the spring constant K. The force of the spring is going to be equal to negative kx. The reason why I wrote it with a negative sign in here is the compression is in that direction, however the force is in the opposite direction, so I had to write a negative sign there. So as to solving this problem, when the string has been compressed, it has some potential energy, the mass is suddenly released from rest. I see the words energy in here and I say, okay, this is an energy problem. So let's go ahead and write our energies. We can have kinetic energy at some initial point, I'm going to call that 1, and then we can have the potential energy at point 1. So I'm going to call this point 1. That will be equal to the kinetic energy plus the potential energy at any other point 2. And I'm going to choose that point 2 to be where the spring was unstretched. Essentially, at that point, the spring will no longer be applying a force. X naught is going to be equal to 0. At that point, the mass has reached its greatest speed. So it has reached its greatest speed where the string was initially compressed, and that's going to be 0. At that point, all of the spring energy has been converted into kinetic energy. So initially, this mass was released from rest, it says, so the kinetic energy has got to be equal to 0. I know what the potential energy of the spring is, it tells me what that is. And at this second point right here, we have no more spring energy. So all of the energy has been converted over into kinetic energy. I can find the greatest speed that this guy reaches simply by saying, okay, this potential energy is going to be equal to 1/2 mass velocity at point 2 squared. All I've done is I've rewritten the kinetic energy in terms of its velocity, and all I have to do is solve this guy for velocity. So the velocity is going to be equal to 2 times the potential energy of the spring divided by its mass. Take the square of both sides, and I come up with 2 multiplied by 11.5, divide that by the mass of the spring, which is going to be, or mass of the box, 2.5 kilograms, and I come up with 3.03 seconds. So now I've solved for the velocity. For part B, what is the greatest acceleration of the mass, and when does this occur? We know that we can write Newton's second law and say the sum of the forces is going to be equal to the mass of the spring multiplied by its acceleration. The only force acting on the block, this is the sum of the forces for the block, is the spring force, negative kx. That's going to give us an expression for the acceleration. The force of the spring will be the largest when x is the largest. When it's been compressed to its furthest distance. So that's going to be the location that the greatest acceleration occurs. It wants us to find out what that acceleration is and when does it occur. In order to solve for this acceleration, I need to know how far x is. To do that, I know how much energy is in the spring. I know that it has 11.5 joules, and I also know a relationship between how far a spring has been compressed and how much potential energy it had. So I can simply rewrite this guy for x, multiply by both sides by 2, divide both sides by k, and take the square root. And I've simply rearranged this equation to solve for x. I plug all this stuff in. 2 times 11.5 joules. Divide that by my spring constant k, 2,500 newtons per meter. Go ahead and I solve this guy, and I get 0.0959 meters. Now I have to ask myself, do I have to choose the positive root or the negative root? Because I have two of them to choose from. The spring has been compressed, it's in a negative direction, so I have to choose the negative root. This is the location where the spring has been compressed the most. It's also the location where the acceleration is the greatest. I can now solve this guy for acceleration. Say that the acceleration is going to be equal to negative kx divided by the mass. And I'm going to bring that guy just down here to solve it. Acceleration is going to be equal to negative 2,500 newtons per meter. The distance is going to be negative 0.0959 meters. Divide all that guy by the mass, 2.5 kilograms. And I get my acceleration to be 95.9 meters per second squared. A very large acceleration. This problem right here would be a nightmare to solve using Newton's laws. However, if we approach it from the standpoint of energy, it's actually quite easy. What we can do is we can say that there is no friction anywhere in this track, so the energy at point A is going to be equal to the energy at the bottom of the hill, the energy at the top of the hill. It's going to be equal to the energy at B, and it's going to be equal to the energy down there. The energy will be conserved for this entire roller coaster ride. So what we can say is the energy at A must be equal to the energy at B. We can talk about two types of energy here. We don't have any springs, so we can talk about the kinetic energy at A plus the potential energy at A must be equal to the kinetic energy at B plus the potential energy at B. We can make this problem a little bit easier by defining point B to be my 0 point, so y naught is equal to 0. This would be the point where I have no potential energy, and this distance between the top of the roller coaster and B is going to be 13 meters. That's the 25 meters minus the 12 meters there. So by using that definition, then my potential energy at B is going to be equal to 0. I know that the roller coaster starts from rest, so all I have is potential energy at A. That's going to be equal to the kinetic energy at B. So I'm simply going to write the mass times gravity times y, where my y is going to be a positive 13 meters, is equal to 1/2 the mass times the velocity at B squared. Masses are going to cancel out, and I can simply write that the velocity is going to be 2 times gravity times that height right there of 13 meters, quantity's square root. Plug all this stuff in, and I get square root of 2. Gravity's going to be 9.8. The height's going to be 13 meters, and I'm going to come up with 15.96 meters per second. For part B, it's asking me how hard it presses against the track at point B. So to do that, I need to first draw the free body diagram of the cart at point B, and I know that it is going to be accelerating in the downwards direction. It's accelerating in that direction, so all the forces, or the force that is accelerating it, that's going to be the force of the track against it, or the normal force is also in that direction. And last but not least, I always have my weight. I always have my mass times gravity in the downwards direction. All three of these guys are pointing in the downwards direction. I'm going to choose down to be positive here. I write Newton's second law. Sum of the forces is going to be equal to the mass times the acceleration. That's going to be equal to the normal force plus the mass times gravity. I'm solving for the normal force, so normal force is going to be equal to the mass times the acceleration minus the mass times gravity. I factor out a mass, and I have acceleration minus gravity. I know what the acceleration is. The acceleration is radial, so I'm going to say the normal force is going to be equal to the mass multiplied by v squared divided by the radius minus g. I plug all that stuff in. I get 350 kilograms. I know how fast it's going from the earlier part, so 15.96 going to be squared. What is the radius of the sky? It's not going to be 12 meters, it's going to be half that. The radius is going to be 6 meters. So divide that by my radius, that's my 6 meters, minus 9.8. And I'm going to come up with my normal force being equal to 11,428 newtons. So in this problem I have a block of wood that is sliding down a ramp. The block of wood is initially at some height. I know that that's going to be 4 meters high. Then it's going to enter at the bottom, very bottom of the ramp, kind of a rough surface. So I'm going to talk about 3 regions here. I'm going to talk about the initial position of the block. I'm going to talk about just before it enters the rough surface. Lastly, I'm going to talk about 3, which is where the block finally comes to a complete rest. Draw a block over here, my velocity equal to 0. And what I'm interested in is what is that distance? I'm going to call it S. Between points 1 and point 2, there is no friction. So I can use conservation of energy and say the energy at 1 must be equal to the energy at 2. If I define my 0 point to be right there, just at the bottom of the ramp, then at point 1, all I have is potential energy. It says the block's initially at rest, my kinetic energy is equal to 0. At point 2, all I have is kinetic energy. I have no potential energy because I've defined that to be my 0 point. And I know that the potential energy can simply be written as mass times gravity times height. That's going to be equal to my kinetic energy at point 2. I know what the mass is. The mass is going to be 2 kilograms. I know what gravity is. That's 9.8. And I know that the height was 4 meters. So I go ahead and I peck all that into my calculator, and I come up with 78.4 joules. Now let's talk about what goes on between points 2 and points 3. I know that now we have friction. Friction is going to oppose motion. Friction is going to be in the backwards direction, acting on this block as it moves from right until left. Friction is not gravity. Friction is a non-conservative force. So I can no longer write the energy at 2 is equal to the energy at 3, but what I can do is I can use that work energy theorem to say the kinetic energy at 2 plus the potential energy at 2, I know that's equal to 0. Well, I'll go ahead and write it. Potential energy at 2 plus the work done by other forces, that's going to be due to friction, must be equal to the kinetic energy at 3 plus the potential energy at 3. And as I said, I've defined my system such that the potential energy is going to be 0 for both of these guys. Now let's talk about that work due to other things. That work other is going to be, in this case, friction. So the work done by friction, which is going to be equal to the force of friction dotted with the displacement. The dot product is very important because friction and S are in opposite directions, so cosine of 180 is going to give me a negative sign. So negative force of friction multiplied by S now. The force of friction is going to be mu sub k multiplied by the normal force being mass times gravity. Now I got my position in there. So I can go ahead and say I know that the kinetic energy at 2 is going to be 78.4 minus the work done by friction, I forgot my minus sign, u sub k multiplied by the mass multiplied by gravity multiplied by S is going to be equal to the kinetic energy at 3. This block has no kinetic energy. It's not moving anymore at 3. So all that stuff is going to be equal to 0. I solve this guy now for S, and I say S is going to be equal to 78.4 divided by mu sub k divided by mass and gravity. So 78.4 mu sub k is equal to 0.2. The mass is going to be 2 kilograms. Gravity is 9.8 meters per second squared. So at the end of the day, I'm going to come up with 20 meters. That's how far, can't forget my units, that's how far the block is going to travel before it comes to a complete stop. The very last part of this problem, part number B, asks how much work was done by friction. I know that the work done by friction is going to simply be equal to the negative kinetic energy. So the work done by friction is going to be negative 78.4 joules.